Welcome to this presentation on configuring customized products with design optimization and value-driven design. The work presented here has been conducted by me, Olle Widner, Camilla Velin, Johan A. Persson, and Johan Elvander. Configuring and delivering customer-unique products can be a time-consuming and error-prone process. It might take many iterations of manual work before even a reliable quotation can be made. Introducing a product configuration system is one common and efficient way to implement mass customization and to tackle these issues. That is, a system where the customer can enter how they want their custom product to be configured. But what if the solution to the customer's problem is non-trivial to define? If it is easier to define the problem, why don't we do that and let a computer do the heavy lifting for us? This is an important part of our approach. We propose a configuration system architecture where a user, for instance a sales representative or the customer themselves, can supply their product requirements to the configurator, that is, a fully automated computer program, and get back evaluated high-quality configurations to act upon. More specifically, we suggest this internal process to be carried out using optimization. By taking in the requirements in a known, structured format, they can be pre-processed by the configurator and be reformulated into an optimization problem. After solving the problem, the dataset of solutions can be post-processed to represent the configurations. Do note that the configuration system does not make the final decision on a specific configuration to choose. We leave that decision up to a human decision maker, but we do want to make sure that the computer helps the user by supplying only a few high-quality configurations to choose from. The basis on which the decision maker acts is not only of a technical nature, but it's also coupled with the configuration's anticipated value. To give an example of how this can be realized, we will now shortly present a case where we define a value-driven configuration process for spiral staircases. The results of executing this process with one specific set of requirements will also be discussed. Spiral staircases are products that are configured uniquely for each customer. They are typically configured with a set of standard components, for instance steps from a set of predefined radii, as well as customized components, such as railings. The configuration process needs to consider a number of geometrical, ergonomical, and regulational requirements, making it a non-trivial task to find feasible design solutions. On the other hand, these requirements are well defined, lending the product well for this approach. The optimization formulation used to solve this configuration problem consists of 4 different computational models represented in this XDSM diagram. This also shows the models' dependencies to each other and to the design variables. The most interesting aspect of this model architecture is the value model, which encapsulates the calculation of a certain configuration's surplus value, defined as the arithmetic difference between its reservation price and its manufacturing costs. This is what one would want to maximize. In our optimization study, we have implicitly done so by maximizing the reservation price and minimizing the manufacturing costs, subject to geometrical constraints. Using this bi-objective formulation gives a broader set of solutions and gives further insights into the trade-off between the value terms. We will now look at the results of executing the formulation with data based on a real-life configuration problem for a 3-floor staircase, and compare it with a manually made baseline design. Executing the optimization formulation over the course of 52 individuals through 50 generations resulted in a design set of 2,600 designs. Plotting these designs in objective space shows that the majority of points evaluated are close to or leading up to the emergent Pareto frontier, with the utopian point in the lower right corner. The values are normalized relative to a baseline design. From this complete dataset, the feasible design subset has been extracted, meaning that these designs satisfy all optimization constraints and also have a positive surplus value. Plotting these 1,381 designs, again in objective space, shows that the optimization has successfully found feasible designs dominating the baseline design. Grouping these feasible designs per staircase radius value and then selecting the designs with the highest surplus value in each one of these groups gives the designs A to E, as shown in this table. To conclude the work, we have presented a framework for integrating design optimization and value-driven design in product configuration systems. In the spiral staircase example presented here, it has been shown to produce designs that resemble and even dominate the baseline design in a fraction of the time needed to do this manually. We believe that this shows great potential to rationalize the quotation process for customized products. Finally, we welcome future research into how this framework can be applied onto products with more complex life cycles, where we believe it to have even greater potential. Thank you for your interest in this presentation and our work.